right, kiddos, we're back. We're going to shift gears again. We're going to get away from some math like we've been doing with our molarity, molality, weight percent calculations. And we're going to talk about something called net ionic equations today. And we're going to learn our solubility rules. Well, we're actually going to start to learn our solubility rules. This is one of those things in chemistry that you see a lot of, so pay particular attention. I'm going to ask you to memorize some things today, so make sure, actually over the next few weeks, you learn these solubility rules. So here are the solubility rules. They will help us write molecular, ionic, and something called net ionic equations. And you're going to see me do several examples. In fact, a couple of demonstrations in this video today as well. Now remember we said that ionic compounds are generally soluble in water. Remember we talked about like dissolves like, and since ionic compounds have positive and negative ends, they're soluble in water. Well, that's not completely true. Most ionic compounds are, but there's some that are not. Turns out that the ions are more attracted to each other than they are to water. Remember, when the solvation process occurs, water molecules surround the positive and negative ions and sort of move away from the crystal structure and allow those ions to flow past one another. Well, some ions are more attracted to each other than they are to the water molecules. So I'm going to talk about them today as I go through your solubility rules. So, the first solubility rule, we'll call this number 1, says that all ionic compounds that contain members of group 1 or ammonium ions are soluble. So Li plus, sodium plus, K plus, NH4 plus. Doesn't make a difference who they're bonded to, who their counter ion is. Those will dissolve in water quite easily. So if I had lithium chloride, or if I had sodium sulfate, or if I had potassium iodide, everything, so long as it's a group 1 ion or ammonium, will be soluble in water. Rule number 2 tells us that if it contains acetate or nitrate ions as the negative ion, those will always be soluble in water. So if I had silver nitrate, it would be soluble in water. If I had lead 2 acetate, it would be soluble in water. If it contains an acetate or a nitrate ion, those ionic compounds will dissolve in water. Rule number 3. Most chlorides, bromides, and iodides are soluble in water. Now, there are 3 big exceptions to that: silver, mercury, and lead. So if I have silver, mercury, or lead chloride, silver, mercury, or lead bromide, silver, mercury, or lead iodide, those compounds will not be soluble in water. But all other chlorides, bromides, and iodides will be. So if I had zinc chloride, I would expect it to dissolve in water. If I had cesium iodide, I would expect that to dissolve in water. If I had manganese 2 bromide, I would expect that to dissolve in water. So almost all chlorides, bromides, and iodides are soluble except for silver, mercury, and lead. And you'll see that that goes for the mercury 2 plus ion as well. All right, sulfates. Rule number 4. Almost all sulfates are soluble. Now there are exceptions. The silver, mercury, and lead sulfates are not soluble, but along with them are calcium, strontium, and barium sulfate. Those will not dissolve in water, but all other sulfates will. If I had a copper sulfate compound, I would expect it to dissolve in water. If I had calcium sulfate, however, it's one of the exceptions here, I would expect it not to dissolve in water. Now, the rest of these solubility rules are mostly insoluble. In fact, you'll see that they're pretty darn similar to each other. So the carbonate, phosphate, sulfide, and hydroxide rules are very similar. So carbonate, phosphate, and sulfide first, we're going to call that rule number 5. They are insoluble except for if they're group 1 carbonates, phosphates, or sulfides, or ammonium. So this applies back to rule number 1. Okay, but all other carbonates, phosphates, and sulfides we would not expect to dissolve in water. So if I had manganese 2 sulfide, I would expect it not to dissolve in water. But if I had cesium sulfide, cesium's in group 1, I would expect it to dissolve in water. And the last rule, which is pretty similar to the carbonate, phosphate, and sulfide rule, is the hydroxide rule, where they are also mostly insoluble, except for the group 1 hydroxides, and then calcium, strontium, and barium hydroxide will also dissolve in water. So we're going to practice these, and just because we do so many problems that involve the solubility rules, you will end up memorizing them just because you hear it so often. But you should take some time over the next few days and learn these solubility rules. You'll see we use them quite a bit. Okay? So, how does this apply to chemistry? Well, let's say that we have 2 different solutions. So we have lead nitrate and sodium iodide. Now, lead nitrate, according to my solubility rules, there's a nitrate in it. It is soluble. And sodium iodide, well, let's see, there's sodium in sodium iodide, and all sodium compounds are soluble. So if they were in separate beakers, lead nitrate would dissolve very, very well in water, and so would sodium iodide. But what would happen if we mix them together in one big beaker? Yeah, then we would have these ions maybe being more attracted to each other than they are to the water molecules. We would have double replacement reactions that might occur. So, what if lead and iodide were placed in the same beaker? Well, according to our solubility rules, let me clear this up a little bit. It's getting a little bit claustrophobic there. So, according to our solubility rules, here's the iodide rule. And it says most iodides are soluble except when they start messing around with lead, mercury, or silver. So lead and iodide would actually be attracted to each other in that solution, and they would form a solid. We call that solid a precipitate. Now, what about these sodiums and nitrates? Yeah, they're not going to be attracted to each other. All sodiums are soluble, all nitrates are soluble, so they would stay in solution. They would be called spectator ions. They'd sort of watch the lead and the iodide react together and form that solid. So let me do one example for you of a molecular ionic and net ionic equation, and then I'm going to show you a demonstration where I'll actually take different mixtures, mix them together, and we will write the molecular ionic and net ionic equations for those. And then in the next video, we'll do some more as practice. So let's say I had a beaker that contained sodium chloride and another beaker that contained silver nitrate. And I want to mix them together. And I want to write the molecular ionic and net ionic equation for what happens there. So let's write down my ions involved first. Doesn't sodium chloride, doesn't that solution contain sodium ions and chloride ions? And silver nitrate, doesn't that contain silver ions and nitrate ions? Now that's going to help me write my formulas in the molecular equation. So sodium chloride is NaCl. Now we know that that dissolves in water, so I'm going to put the letters AQ after that, meaning that water molecules can surround those ions and dissolve the sodium chloride crystal. And I'll do the same for silver nitrate. Silver's 1 plus, nitrate's 1 negative, and that's also, according to my solubility rules, soluble in water. Now, these are all double replacement reactions. So sodium and silver will switch partners. So sodium will get together with nitrate. Sodium's positive 1, nitrate's negative 1. I'm going to leave those parentheses blank for just a minute. And silver will get together with chloride. Remember, we like to write the positive ion first. Silver's positive 1, chloride's negative 1, so we form AgCl. Now, to decide what goes in these parentheses, we have to use our solubility rules. So, for sodium nitrate, we can use either rule number 1, which contains sodium, or rule number 2, which contains nitrates, and they say that those are always soluble. So I can put an AQ after that, meaning that water molecules will be able to surround those ions and dissolve that crystal. Now silver chloride, there's a stray negative sign there I'm going to get rid of. Okay, silver chloride, let's take a look at the solubility rules for chlorides. It says most chlorides, bromides, and iodides are soluble except for silver, mercury, and lead chloride. So that's not soluble, so I'm going to put the letter S after that. Now that S means it will form a solid when I mix those solutions together. Now I balance my molecular, and it's balanced as it's written. So let's write this ionically, as they really are inside my beakers. So sodium Na plus will be surrounded by water molecules, and so will the Cl negatives. Silver ions will be surrounded by water, and so will the nitrates. On the product side, sodium nitrates AQ, so that means the sodium ions and the nitrate ions will be surrounded by water, but AgCl has an S after it. That means I cannot separate it into its ions. We will have a solid forming, a precipitate forming in my solution. It will get cloudy, sort of like this picture up above where it shows sodium copper 2 chloride and sodium hydroxide mixing together. We form a precipitate of copper 2 hydroxide. This would be a precipitate of silver chloride. Now, my net ionic equation is simply the ionic equation with things that are identical on both sides of the equation being crossed off. So I'm going to go ahead and change colors on my pen here. And we're going to cross off what we call the spectator ions, the ones that are the same before and after the reaction. So Na plus AQ is the same on both sides. And what else? Oh, the NO3 negatives are the same on both sides. Now I can't cross off the Cl negatives because they're bonded to silver on the other side, and I can't cross off the Ag pluses because they're bonded to the chlorides on the other side. So they are not spectators. So I include those in my net ionic. So let's go back to my pink color and write my net ionic, which would involve everything that I did not cross off. And I always put the positive one first. So we have Ag plus AQ reacts with Cl negatives AQ to form AgCl solid. And this is called my net ionic equation. That's what actually happens during the reaction. Okay, at the end of this video, I'm going to show a demonstration where I do a couple of different mixtures, and I'm going to write the molecular, ionic, and net ionic equations for those reactions that take place. So enjoy that, and then the next video that we do, we'll do some more examples for you. All right? Enjoy the demo. Bye-bye. Okay, quick demo today, and maybe a little lesson as well. What we're going to do is we're going to talk quickly about net ionic equations, and I'm going to show you guys a couple of double replacement precipitation reactions. So we have sodium iodide in solution and lead 2 nitrate in solution. I place some sodium iodide in this beaker, and we're going to react sodium iodide. AQ means it's dissolved in water, which you can see it is. And lead 2 nitrate, AQ, dissolved in water. Voila, there it is. And I claim when they react together, I'll form sodium nitrate, which should stay in solution, and lead 2 iodide, solid, so a precipitate will form. Now I know that's going to be a solid based upon my solubility rules, which you guys should have learned by now. So let's go ahead. Here's my beaker of sodium iodide. We'll get a little aerial view here. I think it looks sort of cool to watch it this way. And we'll put a drop in there. And it's sort of fun to see that nice yellow precipitate spread out in the beaker. So that's lead 2 nitrate reacting with sodium iodide. So let's take a look. Maybe we'll see a side view here. See if that looks even more fun. Nice, pretty precipitate forming there. Okay. Now, what I've also done for you is I wrote the ionic reaction, where we have 2 sodium ions and 2 iodide ions dissociated, a lead ion and 2 nitrates dissociated. That's what AQ means again. Those ions dissociate in water. The sodium and nitrates stay dissociated. They are not. They are soluble in water, and the PbI2 sticks together. It is insoluble in water, so it's a solid. I'm going to cross off the spectators for you real quick, and we'll have what we call a net ionic. So I have 2 sodiums on both sides, so they're gone. And what are the other spectators? Do you guys see them? That's right, the 2 nitrates, they're gone. So we have the lead ions and the iodide ions remaining, along with PbI2 solid. And so we call whatever's left the net ionic. Do you like that? I'll do another one real quick for you. So we're going to take sodium carbonate and calcium chloride, and we're going to form sodium chloride and calcium carbonate, another cute little double replacement reaction. So here I have some sodium carbonate that's been dissolved. It's in my beaker here. You can see that it's AQ, dissolves very well in water, and my calcium chloride, which also is AQ. So we'll do the same thing. We'll do the side view first here, see if you guys like that better. Let's see here, I'll put a couple drops in. And this one's not nearly as pronounced or as pretty as the other. Put a little bit more in there, and you can see it's start off a little gelatinous precipitate there. Let's take a look. We'll put some more in there, and now we'll go from up above, and you can see the nice precipitate that's formed, and that precipitate is my calcium carbonate. Now, calcium carbonate, of course, is just chalk dust. So if I swirl that around, I'll let that settle out for a while, and you'd end up with a white powdery layer on the bottom, and then of course the aqueous layer up above. So we can write the ionic equation. 2 sodiums and my carbonate are dissociated from each other. A calcium and 2 chlorides are dissociated from one another, and I form 2 sodiums and 2 chlorides dissociated from one another, and a calcium carbonate that sticks together. It's insoluble. So let's cross off our spectators again. And it looks like sodium is the same on both sides. And what else is the same? Good job. The 2 chlorides are the same on both sides. The calcium and carbonates are stuck together on the other side. So we write whatever's left over, and you'll notice I like to write the positive ion first, just out of habit, and then my negative ion with my solid afterwards. So that's how you write molecular, ionic, and net ionic equations, and these are both for nice little precipitation reactions. Hope you enjoyed it. Bye-bye.